We've been using functions to model data, and the three types of functions we've been working with are linear functions, quadratic functions, and exponential functions. But if we're given a set of data, how can we choose which of those three functions would be the best fit or the best model for the data? Let's review the main characteristics for each type of function. Linear functions are going to be in the basic form y equals something times x plus something. You probably learned in Algebra 1 y equals mx plus b. Well, what does it look like when you graph a linear function? It looks like a line. You see the word line built right into linear, right? So the main characteristic of a line is the consistency of the way the y values change, right? It's going up by the same amount each time here, right? Let me pick a nice easy number so that we can see. Let me change this to, let's say, 2. If I look at the table of values here, you'll see as the x values change, what do the y values always change by? Every single time the y value goes up by 2, right? Plus 2, plus 2, plus 2, plus 2. There's that consistency. That's what makes it linear. So if we're looking at a set of data and we're trying to decide if it's linear, you should see that the y values are basically changing by the same amount every single time. What about quadratic? Well, quadratic equations are characterized by having an x squared in them. So it's something times x squared plus something x plus something. In the graph, we said it's called a parabola. It's this U-shaped thing. The characteristic of the graph is a smooth gradual curve that reaches a vertex point, like a low point down here, and then comes back up gradually on the other side. And it's symmetrical on each side of that vertex. And it could be going the other way, right? It could be rising gradually up to that vertex point and then dropping on the other side. So what does this look like in a table? Well, you're going to see some kind of symmetry in it, right? Like if you look at the numbers here, you see that from negative 3.8 to negative 0.7, it's going up, right? It's getting closer to 0, less negative. Then it goes up to positive 1, then it goes up to 1.3. So it's going up by a little bit less. Now it's only going up by 0.3. And then it starts to go back down, right? From 1.3, it goes down to 0.2. Then it drops all the way to negative 2.3. Then it drops all the way to negative 6.2. And so it's dropping more and more. So you see this sort of symmetry where it's going up and then coming back down. All right, well, what about exponential? An exponential function, you remember, is characterized by repeatedly multiplying by the same thing. So the equation is going to be some number to the power of x. If that number, that base, is something bigger than 1, make this positive real quick, then it's going to be what we call exponential growth. It's going to be growing slowly and then quickly. If the base is smaller than 1, it's going to be exponential decay. It's going to be dropping quickly and then slowly. Let's look at a table and see what that would look like. And I'm going to make these numbers just a little bit bigger so it's a little bit easier to see. So how does exponential growth look on a graph, or rather on a table? Well, you can see that it starts off going up by a little bit. Goes up by just a little over 1, then it goes up by almost 4, and then almost a little bit over 7. But then and now it's going up, by the end here by 200 at a time. So it grows slowly and then quickly. Whereas exponential decay, if we bring this down to let's say 0.6, you're going to see exactly the opposite. It's going to start big. Let's start even bigger, actually. And you can see it drops by 40, then it drops by 24, and then it's going to drop less and less. By the end, it's dropping hardly at all. Let's do some example problems and see if we can figure out the best possible function to model our set of data. So what do you think about this set of data here? We've got a bunch of data values. Do you think that this looks like it's following a linear, a quadratic, or an exponential pattern? Remember, a linear model would be basically a line. Quadratic, you should see something of a U-shaped curve. Exponential, you should see it growing gradually or slowly and then quickly, or dropping quickly and then slowly. Well, this very much looks like a line to me. You could pretty much draw a straight line through it. So this is very clearly linear. All right, let's look at this set of data here. What do we think? Well, as the x values are going up, as the year's going up, how's the population changing? Well, it goes up by about 10 the first time, and then it goes up by over 200, and then it goes up by a huge amount there, right? Over 1,000, and then over 5,000. So it looks like it's growing slowly and then quickly. So this looks like it's exponential. Now, if you're not sure, you can always put this into a table in Desmos and get some confirmation here. So let's do that just to get a visual and to get some confirmation. All right, so there's my data. I'm going to hit the little magnifying glass so I can see it. This very much looks like an exponential curve. Let's add a regression to see. Linear, that's okay, 0.56, 0.57. Quadratic, pretty good, 0.8991. But I'm going to guess that exponential is going to be super good. 0.9993, 0.9996 if we put log mode on. So this is definitely an exponential function. All right, here's another population growth one. So we can see here as the years are going up by 1, how's the population changing? Well, it goes up by 3 the first year, and then it goes up by 4, and then by 3 again, and then by 4, and then by 1. So it's pretty consistent. It's going up, except for that last year, it's going up by the same amount every single time. So maybe it's linear, but that last one makes me wonder, is it quadratic? Because it was going up by more at the beginning, and now it's kind of leveling off a bit. Maybe it's reaching kind of a vertex point there at the top. It's definitely not exponential because we don't see any big increase, big growth, or big decline. Let's put this into a table and get a look and see which is the better fit, linear or quadratic. All right, so put the table in, hit the magnifying glass, and yeah, see, it looks almost exactly like a line except for that very end there. Let's see how good the linear fit is for it. 0.98, that's really, really, really good. Quadratic, 0.99, slightly better, but I mean, quadratic will always be a little bit better than linear because if you think about it, if you just make this first part, the x squared part of the equation, go away, if I just made that 0, then all I would have left is a linear function at the end, right? You got a number times x plus a number. This part's linear over here, right? So it's impossible for linear to actually be better than quadratic, but let's see what our answer choices are. We know it's not exponential, so it's not going to be this one. This is an exponential function because it's something to the power of x. These three are linear, and this one is quadratic. Is this the same equation that we have right here? It's not, because you see here it's got a negative sign with the 4.42 instead of a positive. So they must be saying this is linear. Let's go back to linear, and it should be 3.17, positive 3.17 plus 10. So that would be this answer.